right, hoping everyone is ready here. So, class, Christian. Wow, is it just one of those days? You feel nauseous? That sucks. I heard there's a protest outside right now too.
It's a chill one.
It's a chill one?
They're playing Katy Perry and holding signs like everyone is safe here or something. It's, I think, a bunch of parents. It's the union.
It's the what?
The union.
It's the union. Oh. So it's like employees and stuff?
Yeah.
Oh, okay.
Teachers and stuff. Union people? They have union shirts on.
Oh.
Oh, I didn't see that. Oh, that's
Oh.
really cool.
So. Alrighty. Okay. Alright, so let's see. Concave up, concave down. So up until this point we've been throwing up gang signs and actually using the first derivative. Let f be a function that is continuous on the closed interval from a to b, differentiable from a to b. F is concave up on the interval if the graph lies above each of its tangent lines through a to b. So, concave up if the graph of f above each of its tangent lines through this. F is concave down on a to b if the graph f lies below each of its tangent lines through a to b. Now, does that make a whole lot of sense? Probably not, right? So, let's look at it like this. Test for concavity. So now we could actually test concavity instead of actually just plugging in to a number line. F be a function is continuous on the closed interval from a to b. Suppose f prime and f double prime exist on the open interval from a to b. So if f double prime is positive on the interval, then it's concave up. So, bam. So if I find the derivative, okay, I get a critical point. And then I take a second derivative at that point. If it's positive, it's concave up. If it's negative, it's concave down. So we use our first derivative to get my critical points. And how do I do that? Juju Bear, how do I get a critical point?
Set equal to 0.
Mm-hmm. Set it equals 0, good. So is there any others that would be a critical? Undefined, very good. So where my derivative is undefined also. So, all right. So those two places are my critical points, and those are given from my first derivative. Now we take those values and plug them into the second derivative. Positive, concave up, negative, concave down. Show that f of x equals e to the x is concave up on its domain, where it exists. Okay, so let's see. I get f prime of x equals, what's the derivative of e to the x? E to the x. Okay, now set it equal to 0. Okay. So e to the x equals 0. Is there like a weird log rule or something I could do to try and do this? How do I undo an e? What's the opposite of e? Natural log, very good. So I'm going to ln both sides. So natural log both sides. So that's going to give me ln of 0 is equal to x. What is ln of 0? Let's see. Okay. because there's a whole lot of ln rules that a lot of people struggle with. So I'm just going to pull out my calculator so we can see this. All right, so we're talking about e to the x, right? There's my graph. Okay. All right, so I want to know, when is that equal to 0? At 1? No. It's not at 1. Look at it. Is there any place in which that this is actually going to become 0? So let's go ahead and trace this. Menu, trace graph. So I want not 0. I'm not plugging in 0. I want my y value to be 0. What's happening there? Yep, it's an asymptote. So is it ever equal to 0? No, it's never equal to 0. So there is no places in which that this is going to be equal to 0. Okay, so that's helpful. Okay. Okay, so this is going to be none, right? So I don't have any places where it's equal to 0. So that means that it's all going to be the same thing. So now concave up, concave down. So I could pick a point inside that interval because I don't have any critical points. It's going to be everything. Okay, it's all my values. All the values are what I'm going to use. So let's pick a number. Let's pick a number. Let's go with 1. Why not? So the second derivative, f double prime of x, is e to the x and using second derivative test, so I'm going to say that f double prime of 1 e to the 1. And now I'm testing this. What is e to the first power? It's like 2.7 something. Is that positive or negative? It's positive. So if it's positive, what's the concavity? Concavity, yeah, it's concave up. So I can pick just about any number there, and I'm still going to get a concave up. Actually, not just about, it's all numbers that I pick on that. It's going to give me concave up for my second derivative. Does that make sense? Hopefully? Okay. Find any local extrema of the function. So let's start off by factor that. F prime x equals 3x squared minus 12x plus 9. And my favorite thing to do every time I look at one of those problems is just say what? What would you say when you look at a problem like that? I think you say it the most. You say F that. Right? Yeah. So factor it, right? See what I did there? Factor. Factor. Okay. All right, so factor, what can I factor out? A 3? So 3 quantity set equals 0, that 3 is going to go away, but then I still have to factor the others. Multiply to be positive 3, but add together to be negative 4. If it has to multiply to be positive 3, that means I need to have same signs. So it's a positive positive or a negative negative. What do we got? Negative 1 and negative 3. So, right here, this is going to give me critical points. X equals positive 1 and positive 3. Okay. So, using that, I have my critical points. And now I could test my critical points where? Second derivative? Okay, so let's take my derivative and do the second derivative. So f double prime of x is going to be equal to 6x minus 12. Factor, I get 6x minus 2. And if I plug in my critical points, if we plug in a positive 1, at positive 1, I'm going to get a positive times a negative. So that's a negative. So that means if that's a negative, this has to be concave, concave down, right? Throw up that gang sign. If it's concave down, what do I have at 1? What type of point do I have at 1? Is that going to be a min or a max? That's going to be a maximum. Because if it's negative, it's concave down. That's why I throw it up those gang signs. Concave down is going to give me a maximum at 1. So there's a local max at 1. And now I'm going to do it again for 3. So plug in 3, I get 3 minus 2 is positive 1 times 6, so positive, positive, that's a positive. So given positive, throw up that gang sign, I have a positive concavity. Right here, this gives me a minimum. So therefore, I have a local minimum at x equals 3. Now, if I were to write step-by-step instructions, what would I start this off with? What do we do here? Find the derivative, right? Set the derivative equal to 0 to get my critical points. Okay. Find the second derivative, and then plug in my critical points into my second derivative. So hopefully that's not too bad, right? Inflection points. Suppose that f is a function that's differentiable on an open interval from a to b containing c. The concavity of f changes at the point c, comma, f of c. Then c, f of c is a point of inflection. Now, throwing up little gang signs again. So, right here, so in between my two concavities, a concave up, concave down, that is my point of inflection. Okay? Now, think about this carefully. If it's concave up, what type of number do I have for concave up? That's a, what do we say here? It's a positive, right? And if it's concave down, that would be a And what happens in between changing from a positive to a negative? 0. That's where I get my points of inflection. Points of inflection is my second derivative equal to 0. That's where I get my points of inflection. My second derivative equal to 0. Alright. Let f denote a function that is differentiable on the open interval a to b containing c. C, f of c is the inflection point of f. Then f double prime of c equals 0, or f double prime does not exist. Now, why did I use that? Why did I not say that part right there? Because when we're looking at our concavity, for my concavity's got to change, okay, it's got to be an inflection point, it's got to change from positive to negative, right? So, it must also go from there to actually change concavity, or does not exist, which is also going to happen at the same thing. So when I'm looking at it, it's still going to have to change there. So it has to change from one to the other. You can't just go from concave down to concave down at any point. Because sometimes we are going to have points in which that second derivative is equal to 0, but on both sides it's going to be down. So it's just changing the rate. So, anyway. Step 1, find all numbers domain f del prime equals 0 or at which that does not exist. Step 2, test for concavity, determining concavity of f, both sides of each of these numbers. Step 3, if the concavity changes, there is inflection point, otherwise there is no inflection point. Right there. If it changes. If it changes. Otherwise there's no inflection point. And let's see, how many more slides do I have? Wow. That was loading for a very long time.
9, I think.
9 more slides?
Yeah.
Okay. So I'll do this one, and then from there we'll go through and use the rest of time for homework. Okay? Alright, continue here. Find all inflection points. So, first thing I'm going to do is f prime of x equals 5/3 x to the 2/3. So, set it equals 0. Since this is a third root, that's what that 3 on the bottom means. It's a third root. If it was a square root, I would have to deal with, I cannot have negative numbers. If it was a fourth root, again, I cannot have negative numbers. Because that goes, the rule with, there's no negative inside a square root, right? You get imaginary numbers. Same thing goes if this was a 4, or a 6, or an 8. So any even number root, like this, you cannot have negative numbers. But since this is an odd number, you're allowed to have negatives. So it could be negative. So let's go ahead here, set it equals 0, divide both sides by 5/3, I get 0 equals x. Okay, so how do I undo that power? There's some algebra right here. How do I undo that power? Oh, if I rewrite it like this, hold on. This might actually help. So cube root of x squared. How do I undo that power? How do I undo a square? Oh, square root both sides, right? And how do I undo a root? I take it to that power, right? So I would raise this over here to the, backwards. So 0 to 3 halves is still 0 equals x. So I only have one critical point here. One critical point. Now let's find the second derivative here. So f double prime of x is going to be equal to, let's see, that would be 10 over 9 x to the negative 1/3. Alright, so from here, set this one equals 0, and I have 10 over 9, come on, work, x negative 1/3, so I can put that x on the bottom. So what is it going to give me at 0 now? 0 is now undefined. Okay, since 0 is going to be undefined, I only have 0 as a critical point and 0 as undefined. What can I use now to actually check my concavity there? Can I go back to first derivative? Yes, you can. Because we have first derivative. If I do first derivative, just plug in numbers that I had. Plug in numbers to see what my slope is on either side. So let's see, at negative 1, if I plug that into my derivative here, going back up here, plug that in, negative 1, so that's going to give me a positive because I'm squaring a negative 1. Cube root of 1 is 1, so that's going to give me a positive. Do the same thing at over here at 2, I'm sorry, at 1, positive 1, I get the same thing also, it's positive. So I have positive, positive. What does that tell me about that? So let's go over here. Doc B. And it was x raised to 5/3. So it looks like we do have a point of inflection there, where it's changing from concave up to concave down, but my slope is all positive from here to here. Now let's graph our derivative, which was x raised to 2/3. So there's my first derivative test. The red line, everything is positive here, right? And over here on the right hand side, everything is positive. So given that, I have positive, positive, so everything's positive, but right here, it's going to be, I can't take a derivative at that point. That is what type of point there? Cusp. Okay. A pointy point. There's my cusp. And then from there, I could actually look to see, from here it looks like my original graph, it looks like this is all concave down, and this is all going to be concave up. So I could actually use second derivative also to test at those same points. So f double prime so if I'm using second derivative, plug in -1. If I plug in -1, that's going to give me a negative right here, because I'm plugging into this. It's going to give me a negative, because I'm allowed to have negatives. Or I could plug in here. Same thing, but cleaned up a little bit. So I could have a -1, so it's a positive over a negative. That means this is negative. And if I plug in +1, the bottom is going to be a positive, and the top is a positive. So that tells me that I have mathematically shown what I have in my graph. From my graph right here, the blue line, on the left side is 0, it's concave down. The right side of 0 is concave up. And if it's changing concavity, that is an inflection point. That's my point of inflection. Questions, concerns, complaints, conspiracy theories? No, I'm just boring everyone to death. Okay, so apologize for that. Alright, so let's use the rest of the time to work on the assignments.